Okay, here we have a presentation, solids of revolution, and this is our washer example number 3. So consider this problem of having the region bounded by these two curves, y equals x and y equals 1/3 x squared, is revolved about the line x equals 5. This gives us a certain solid, and we want to find an integral that we can use to compute the volume of this solid. Okay, in this illustration we see the region here, and it's bounded on its left by y equals x, and on the right by y equals 1/3 x squared. And also here we see the line x equals 5, which is the vertical line that we want to rotate the region about to get a solid. So I get this kind of interesting solid here. Its outer part is a frustum of a cone, and the inner part is a hollowed out volcano-like region. Okay, so we want to approximate the volume of this object using washers, and I can see what it looks like for 4 washers, and if I like, I could add up the volume of each of these washers and I'd get a very crude approximation to the volume of the solid. We get a better approximation if we use more washers. So here I have this with 11 washers. And you can see what this looks like. Here's just another view. You can see from the top. And here's a view from below. Here's what the cross-section looks like if I take a vertical slice of this object, well, actually of the washers. You can see we have the jagged edges here, but we have a rough idea of a line here and a rough idea of a parabola there. Here we have an illustration of the ith washer, where my subscript here is going from 1 to 11 if I have 11 of these guys. And notice each of these washers, we have an inner radius from x equals 5 to this parabola, y equals 1/3 x squared, and we have an outer radius from x equals 5 all the way to this line here, y equals x. And we have a thickness change in y. So our volume here for this ith washer is going to be its cross-section area times its thickness. And the cross-sectional area, I just have the difference in areas between the outer circle and the inner circle. So I get I get pi times capital R sub I squared minus pi little r sub I squared times change in y. Now we need to consider the outer radius. So the outer radius is going from x equals 5 all the way over here to the line y equals x. This point on the line is x sub I, y sub I. And I might notice that my x sub I plus my capital R sub I add up to be 5, because we have the distance going from x equals 0, the y-axis, to this vertical line x equals 5. So I can write this here as x sub I plus capital R sub I equals 5. So capital R sub I is 5 minus x sub I. But y is a variable of integration. And so I want my capital R sub I not in terms of x sub I, but in terms of y sub I. But my x sub I equals y, so I'm on the line y equals x. So I can replace it here and get my capital R sub I is 5 minus y sub I. And we'll use this outer radius in a little bit. So now I consider the inner radius. So I'm going from x equals 5 to the left here to this parabola, y is 1/3 x squared. And I have this down here as well. And just like for capital R, we're going to have our x sub I plus our r sub I is 5. So my r sub I is 5 minus x sub I. But again, I want this in terms of y sub I, not x sub I, because y is the variable of integration. I have this change in y. But on this parabola, I have y sub I is 1/3 x sub I squared. I can easily solve this for x sub I and get x sub I is square root of 3 y sub I. So I put that in place of x sub I there, and I wind up with this formula for the inner radius in terms of y sub I. Now, my volume for this ith washer is going to be pi r sub I squared minus pi little r sub I squared change in y. But now I have all this in terms of y sub I. So this is my ith washer volume. And if I add a bunch of these up, I'll get an approximation to the volume of the actual solid. And for us, n is 11. So here I have, as a sigma notation, the sum I equals 1 to n. And I have this all in terms of y. This is what's called a Riemann sum. And in the limit, as n goes to infinity, I take more and more washers, and they're thinner and thinner. I pass to the definite integral. So y is going from 0 to 3. That's from my region. Instead of having the y sub I here, I have just y here. There's no subscript. And likewise here and here. And then corresponding to the change in y, I have dy. And then if we like, we can evaluate this. It's not a difficult integral. You just square things out and use the power rule and the fundamental theorem of calculus. And it's rather amazing, though, that we could get the volume of this solid using the volumes of just washers. And that's that. Thank you.